So maybe we start now. So this is the third tutorial of this course, and today I am going to discuss about separation theorems. So we have seen that in some of the results discussed by Professor Johan Enrique is this separation theorem is used. So what are the conditions that we can separate two sets? Suppose we have a set like this. Suppose this is one set and another set is like this. So is it possible to find a hyperplane which will separate both these sets? So in one part, because in space, whenever we have a hyperplane that separates the space into two parts. So is it possible to find a hyperplane that will separate so that this set C1 and this set C2 is on the one side of the hyperplane and that set C2 is on the other side of the hyperplane. So if it is possible, then what are the conditions under which we can find such a hyperplane which will separate any two given sets? So you can see that here it is not possible to find a hyperplane. If we draw a hyperplane like this, some part is of the set C2 is on one side, some is on the other side. If you have this one, again the same condition. If you have this, so somehow we are not able to find out a hyperplane which can separate these two sets C1 and C2. So suppose we have some other types of sets that we can have like this disjoint. Although these two sets were also disjoint, C1 and C2, this C1 intersection C2 is this is empty. But we cannot find a hyperplane which will separate these two sets. But in case of this one, suppose C3 and C4, what we can have, we can have this hyperplane which separates this C3 and this is the normal to the hyperplane. So you can see that here in this case we are able to find out a hyperplane which separates the set C3 and C4. So the question is that what are the conditions under which we can find out a hyperplane which will separate these two sets. So one thing is very important, that is the convexity of the sets, because in the last class we have discussed convex sets and different operations that preserves convexity, and we are dealing with convex optimization problems, so the feasible region will be a convex set. So under convexity assumption we can find out hyperplanes which will separate the given sets. So for that we need a property which is known as projection property. Projection property. So what is this projection property? Let C is a subset of Rn, and this set we assume that be non-empty and closed and convex. Closed and convex. Okay. And we assume that there is a point X which does not belongs to C. So this is actually, so okay, I will explain. Then there exists an unique projection let us say P cap in the set C of X, which is a solution of this minimization problem. So minimization problem is P belongs to C and norm of P minus X, and this, so we have Y minus P cap and P cap minus X is greater than equal to 0 for every Y and C. Okay. So this is the problem, and this is the projection property. So what is the thing? Geometrically, we have this set C, and we have a point X which is not in C. So it is outside C, and then from X we can join all the points in C. So there will be some point here which we call the projection of X over C. So, and this point P and any other point in the set which we denote by any P, and we can join this too. So you see that so this is Y minus P. Okay, so it should be Y. So Y is any point in the set C. So whenever, so this is Y minus P P hat, this is the vector, and this is the vector P hat minus X. So it tells that this angle in between these two vectors, this will be always greater than equal to 0, right? So we have this angle is always more than 90 degree. This angle is always greater than 90 degrees. So you can move this vector anywhere in the set because Y is everywhere. And then we can find out a point P hat in this set which will be unique projection, right? So let us try to prove this result, because this result is instrumental in proving the separation theorem. So for the proof we go for this, the first we try to prove the existence. So since this C is non-empty, because this is the assumption of the theorem, therefore we can write this infimum of P minus X, and P belongs to C is less than plus infinity. This will be some finite number. This will be some finite number, and this is also greater than or equal to 0. So this infimum will be some finite number, and since this is outside this set C, this will be greater than equal to 0. Now the proof, we have to find out a sequence which will converge to this infimum. Like we assume that Pn be a sequence in C such that this, so we make another sequence Pn minus X. So if Pn is a sequence in C, then this Pn minus x will be another sequence, and then we can take the norm and that will be another sequence. So this sequence converges to this infimum of this norm of P minus x, and this P belongs to C, right? So this is the usual limit of a sequence. So what we can use the definition of the limit of a sequence, and by using the definition of the limit of a sequence, we can have some natural numbers and such that, so we can write norm of Pn minus x is strictly less than infimum of P minus x plus 1. So in place of epsilon we can take any number, so we can take anything in place of, so we are taking this plus 1 just to fix this number, and P is in C, and this is plus infinity. I mean some finite number for every n greater than equal to this capital N. Okay? This is the definition of limits. For any epsilon greater than 0, there exists some natural number such that an minus x is less than. So we have just used this. We have used this an minus l is less than epsilon, which is equivalent of saying that this an is less than l plus epsilon and greater than l minus epsilon. So that is what we are writing here. This is less than this number l, this is l, and this is epsilon, so we are taking plus 1. So we are using only the definition of this limit. Now this implies that this sequence Pn is bounded, right? Because this number is bounded, so we can use the triangle inequality to show that this norm Pn is less than equal to some finite number. So this sequence is bounded, right? Reverse triangle inequality, so x minus y is greater than equal to norm of x minus norm of y. So by using this, we can show that this Pn is bounded. Now if this Pn is bounded, so we know that every bounded sequence has a subsequence which is convergent. So by using that result, that is, I think, Bolzano-Weierstrass theorem, we can have a subsequence of this Pn which is convergent. So that implies that there exists a subsequence, what we call that P and K 1 to infinity of this sequence Pn which is convergent, right? So when we have this convergent sequence, so there will be some number, that is, we have this P and K converges to some P hat in Rn, right? When this K tends to infinity. So this number will tend to, so this sequence will converge to some number but that number may not be in C. That number may not be in C, but that will be in Rn. But then we can use another property of C that is given, and that property of C is also closed. So since the set C is closed, therefore, so we know that every sequence, the limit will also belongs to that set because C is closed. So this P hat will be in C, right? Now what we can do, we can use the continuity of the norm. So this is P and K minus X will tend to P hat minus X by T property. I mean this P and K is a sequence which is converging to this P hat. So this P and K minus X will be a sequence which is converging to P hat minus X, and then we can apply the property of, so this norm is a continuous function. So the continuous function will preserve the limit of a sequence. So it will go to like this. So P and K minus X with this norm will converge to P hat minus X. But you see, we also have this notion that P and K minus X converges to infimum of P minus X. This P belongs to C. Why? Why it will be like this? Yes, very good. So if a sequence is convergent to a limit, then all its subsequences will be convergent to that same limit. So P and K, since P and K is a subsequence of the sequence Pn, therefore, and Pn converges to this, I mean norm of Pn minus X, so therefore it also converges to this. But you know that this limit of convergence should be unique. So both of these numbers must be same, and therefore by uniqueness of limit, we can write that this P hat minus X is equal to infimum of P minus X, P belongs to C, right? So you see, you have this, so this infimum is attained at this P hat minus X, and this is actually the definition of the projection of a point X over this C. So we can say that P hat is a projection of X over the set C, right? So that implies that P hat is the projection of X over C, right? So this is one thing that we wanted to show, that this is the projection, right? So now we have to show this projection property, that with this point this property must be satisfied. So the property that we wanted to prove now will be proved by using the convexity of the set. So for any y in C and lambda in 0, 1, one has 1 minus lambda, this p hat plus lambda y belongs to C by convexity of C, right? So the first property that we have seen is true without convexity, right? So for projection we can use this. So we haven't used the convexity, but we need the set to be closed. So if the set is closed and non-empty, then we can apply the first result. But then for this property we need the convexity of the set. So since P is the projection of X over C, therefore we can write this P norm minus X is less than or equal to, because from this you see this is the minimum value, right? This is the minimum value we are having. So it means this value will be less than or equal to every value of this norm. So in place of P we can have any other element of the set C, right? So we can write this X should be less than or equal to, so now we are going to write this number 1 minus lambda y minus X, right? And then what we will do, we can put a square over this norm. So with this square, now it is equal. So after rearrangement, this is P hat minus X, and then with this lambda we have, so okay, so y minus P hat, this is square. But this square can be written in terms of inner product. So this is equal to P hat minus X whole square. So like A plus B whole square we can write in terms of inner product. So this is 2 lambda and inner product of minus X and y minus P hat, right? And this is lambda square norm of y minus P hat whole square. Okay. So you see that this number, because this is P minus X whole square and y minus P whole square, so that implies that this number is greater than equal to 2 minus X y minus P hat plus lambda whole square. And now what we can do, we can have this, we can take the limit. Taking the limit as lambda tends to 0 plus 1 has, so this will be 0, so 0 is less than equal to and since this is for any arbitrary y in C, this is for every y in C, right? So this is the property that we wanted to prove, and geometrically we can see that the point which will be the projection, so if we go from that point, from the point outside the set, we can go there, and to any other point in the set, this angle will be more than 90 degrees. Now what about the uniqueness? Uniqueness you can prove by this property, uniqueness. So you can try, let P hat and P tilde be two distinct projections of X over C, right? So what is the thing, that this minimization problem, we are trying to show that this minimization problem will have only one solution. We cannot have more than one projections, right? We cannot have more than one projections. So we have to, but then we have to prove this. So you can use this inequality. You try to solve this, that how we can prove this uniqueness. So this will be proved by using this property. So in place of, so one time this is a point in C, so you can place this in place of y, one time you can place P tilde, and another time you can place, you can exchange that, okay, and then you try to add the inequalities and try to find out, then you will see that this P tilde and P hat will be equal. That is the only way that, so we have this uniqueness. So now with this projection property, we know that if a point is outside of the set and that set is closed, non-empty, closed and convex, then we can find out a projection on that set which is unique. So this projection property can be used to prove a separation of a point and a set, right? So the next result we are going to discuss is a strong separation between a point and a set, right? So the theorem is, let C is a subset of Rn, be a non-empty convex and closed set right, same as before, and we assume that there is a point X in Rn which is not in C, then there exists. So you see how you proceed. You have this set which is closed and non-empty and convex, and then you have a point outside this set, and what we want to do, we want to have a plane which separates this point and this set, right? So this and not only this, actually we can find a plane passing through this x, and we can find a plane which is parallel to this set like this, and both these planes will have the same normal, and then the space in between can be filled like this. So that is why this is a strong separation. So you have a gap in between this set and this point. So what will happen then? There exists some vector A in Rn with, I mean you can have any, but we are taking a unit vector such that this we can write infimum of A y is greater than A of x, inner product, and this y is in C. So again we have many points in this set C, this y, and then we can have this inner product of A and y, and this. So this may represent a hyperplane. Okay, if we have some this inner product of Ax is equal to some number, it may represent a hyperplane. So if we take the infimum of this, that will be always greater than A of x, right? So now we will use this projection theorem to prove this result, or projection property to prove this result. So let P be the projection of x on C, so P hat. Then by the projection property, what we can write, we have this y minus p hat and p hat minus x is greater than equal to 0 for every element y in C. That we have proved now. Now we need a vector which will satisfy that condition, right? So we take a vector A, which we can define like p minus x upon, so this is p hat minus x upon norm of p hat minus x, right? So by this setting, this vector will be a unit vector. So you can see that this A is equal to 1. But now we have to show that this condition is satisfied with this vector. So if we write this A y, so this A y is equal to 1 upon, because this is the vector, so we can write norm of p hat minus x and the inner product p hat minus x and y, right? And this is okay. So this value is actually greater than or equal to, by this property you see, p hat minus x y. This will be greater than or equal to p hat inner product p hat minus x, right? So this is greater than or equal to 1 upon norm of p hat minus x and we have this p hat minus x p hat, right? Okay, and this is true for, so this ay is actually greater than this number. But what is this number again? So this can be rewritten as 1 over p hat minus x, and we can write it as p hat minus x upon p hat minus x, and then we can, because we are subtracting this number, so we can again add this number, minus x 2x, right? By using that inequality. So this is, so what is this? Inner product of the same vectors. So it will induce the norm. So we have this p hat minus x whole square and p hat minus x, right? And this is nothing else but a x. So this number is actually greater than 0 because x is outside the set, and this p hat is the projection of x over the set. So this is always greater than 0, and then what we can write? We can write that which gives, so we have started from this ay. So ay is strictly greater than ax. Ax for every, now this is true for any y because y is arbitrary. So we can do this for any y, so this is true for every y in C. And since this is true for any y, what we can do? This is greater than, so this is also true for infimum of these numbers. We can take the least upper bound, right? So that implies that infimum of ay, where y belongs to C, is actually greater than a of x, right? And this is what we wanted to prove. Vector A. So this is the vector. This is the projection, and then we are taking, this is the vector p hat minus x. So this is the vector, and then we are taking the norm, so it will become a unit vector. So unit vector in this direction. Okay. So from the point outside the set to the projection on the set, and in that direction we are taking the unit vector. Okay. So, but one more thing that we can add to this is because this inequality is strict, so we can find that a point in between. Okay. So there exists some alpha, suppose in R, such that this infimum of ay is greater than alpha, and this is greater than ax, right? Y belongs to C. So this alpha will induce the hyperplane that separates these two sets, right? So what will be the hyperplane? The hyperplane, then this will be the hyperplane H x in Rn such that A of x is equal to alpha, right? So now you can see this is the hyperplane, and what is A? A is the normal to that hyperplane. So actually A signifies the plane which will separate the set to the point which is outside the set. So and that is the, and for this alpha you can find many alpha, this is not unique, in between, right? So you see that this hyperplane will separate the set C and the point x which is not in C, right? So we can find out an alpha like this which will separate whenever the set C is closed, non-empty and convex. And then you can try to, I mean there are many versions of this separation theorem, so you can try to find out, reduce some condition. If there is no convexity, what will happen? If there is no, the set is not closed, what will happen? Right? So there may be many variations of this result. But this is one thing that we have used. Now this result can be used to give you the separation between two convex sets. In a strict separation you have this, strictly. But in strong, I think this equality is also there. Is it?
But in strict, one of the inequalities would be non-strict.
Okay.
But with the strong, it's
Equality?
Equality both places.
Okay. So this is the difference, right? So we have this now. If we have separation of two sets, and then let us see that how we can use this result. So we can have one set like this is C1, and another set like this is C2, and this is the hyperplane with this normal vector. So let C1 and C2 are subsets of Rn. Closed and convex sets, right? But now, along with this non-empty closed and convex sets, we need another property of the sets which must be bounded, and let in Rn or compact in general. So let this C1 be bounded. And then this set C1 intersection C2 is empty, right? There is no common point in between. So then there exists some A in Rn which will give you the unit vector such that we can write this A of y, and you take the infimum of y1 in C1. Okay, maybe we can write y1 to denote a point in C1, and y2 we have supremum A of y2, and y2 is a point in C2, right? So this is the result, and again we can see that if this is the inequality, there will be an alpha in between these two inequalities which will separate C1 and C2. So hyperplane. So by proving this inequality, we can prove that there exists an hyperplane which will separate C1 and C2. So we construct the proof by taking difference of these two sets. So let C be any other set which can be written as difference of C1 and C2, which is defined as y1 minus y2 such that y1 is in C1 and y2 is in C2, right? So you observe that this C is convex and 0 does not belongs to C. Okay? Why? Because C2 is a convex set. If you multiply a convex set with any scalar, it will remain a convex set. C1 is a convex set, and if you add two convex sets, their sum will also be a convex set, right? So by all this algebra of convex sets, this set C is convex. And what is y1? So y1 is in C1 and y2 is in C2, and C1 and intersection C2 is empty. So there will be no points which are common, right? So y1 is never equal to y2. So this will never become 0. So 0 is outside this set, right? So now you have a convex set C and a point outside that set C. So we can apply that separation theorem of a point and a set, right? But there were some other assumptions as well in the result. Do we have the result? Point. Okay. So what were the assumptions? The set C must be, it is convex, but it should be closed and non-empty. So is it non-empty? Yes, because C1 and C2 are sets which are non-empty. So you always have some numbers, so there will be some numbers which is in this set C. So this is non-empty, and this is convex, but now it remain, you have to prove that this set C is also closed, right? So now we have to show that C is closed to apply the previous separation theorem, right? So how we prove that a set is closed? In analysis, you take a sequence and the limit of the sequence must also be in that set. So that the same thing we are going to use. So let you have xn n equal to 1 to infinity, that is be a sequence in C such that this xn converges to some x hat in Rn as n tends to infinity. right? And now we have to show that this x hat is actually in C. So when this x hat will be in C, if it can be written as difference of two elements, one from C1 and other from C2, right? So then there exist sequences. See, xn is a sequence in C. It means the structure of xn will be, it will be difference of one element from C1 and other element from C2. So we can write that there exists sequences xn, let us say xn1, which will be in C1, and xn2 which will be in C2, such that this xn is equal to xn1 minus xn2 for every n in n, right? So there is a sequence in C1 and there is a sequence in C2. And what is the structure of C1? C1 is, there is an extra assumption on C1. Why? Now we will see. Since C1 is bounded, right? So this is a sequence, see, this is a sequence, xn1 is a sequence in C1 and xn2 is a sequence in C2, but it is not necessary that these sequences will be convergent, right? xn is convergent, but xn1 may not be convergent, xn2 may not be convergent. So for convergence we need another assumption that we have imposed on C1. Again we have used it in the previous result. If C1 is bounded, then what will happen? There will be a subsequence of this sequence which will be convergent, right? So we are going to use this. Since C1 is bounded, therefore there will be a subsequence of, so we denote it by x and k, x and k1 of xn1 which will be convergent, right? So we assume that this xn1 converges to some number xn k1 tends to some number x1, say in R, and as k tends to infinity. Again this will be convergent, but now C1 is also closed. So now we can use this condition of C1. Since C1 is closed, therefore this x1 belongs to C1, right? Now what we can do, we can, okay, so now this x1 is like this. Now what remains to show? We have to show that this x1, what about xn2, right? Because this element should also be, because we have proved one element x1. x1 is in C1, but now we have to show that x2 is in C2, right? But for C2 we cannot use the property of boundedness. If we assume C2 is bounded, then it is immediate. Again we can use the same property, but for C2 we have relaxed the property of boundedness. At least one is bounded, other one may not be bounded, right? So what we can do, we can define a sequence x and k2. This is defined like x and k 1 minus x and k, right, which tends to x1 minus x in C2. Okay, so this xn1 is convergent, it goes to x1, and xn k, what is x hat? X hat is the limit of xn, the sequence xn. So we can have a subsequence of xn k, which will also converge to the same limit. So this sequence will converge to this limit, but this limit, this is an element in C1 and this is an element in C. We will see this now, why this is in C, because what we can do, that x hat we can write it like x1 minus x hat, right? So what is x1? This belongs to C1, and what is this? This belongs to C2, right? So the difference will belongs to C. This will belong to C. Why this is in C2? Because this is a sequence in C2 which converges to this. So this C2 is closed, so this must be in C2, right? Now what we have done, we started from a sequence in C, right, which converges to some point x hat, and now we have shown that this x hat belongs to C. Okay, so it means that C is closed. C is closed. Very good. So now when C is closed and C is convex and C is non-empty and 0 does not belongs to C. So what we can use? We can apply the separation theorem, right? So since this C is non-empty, closed and convex, such that this 0 does not belong to C, therefore by the previous separation theorem of a set and a point, by the separation theorem there exists, so there will be some vector A in Rn such that this norm of A is equal to 1, and so now what we can write? We can write that infimum of this A, y is greater than A0, where y belongs to C1 minus C2, that is C, right? We are applying the separation theorem on the set C. And what is this? This will be 0. So this number, and so this y can be written in terms of y1 minus y2. So that implies that infimum of A y1 minus y2 is strictly greater than 0. y1 belongs to C1 and y2 belongs to C2. So if you change the sides, so what will happen? This is minus, it will go to other side A y2. So A y1 is greater than A of y2. Okay, but then this infimum will become supremum because of the negative sign. So you can write the required result, right? So we can write this supremum or infimum of A y1 belongs to C1 is strictly greater than supremum of A y2 belongs to C2, right? And then again, as we have discussed in the previous result, we can have some alpha in between, and that alpha will separate both these sets, right? So you observe that if the sets are not bounded, so this one was the case, bounded, but if these two sets are not bounded, you try to find out two sets which are unbounded, right, but convex. So yeah, this will be the exercise. You try to find out two sets which are convex and unbounded, and then try to find out whether you can separate those two sets or not. So you have to find out two unbounded convex sets which cannot be separated by any hyperplane, because there will be unbounded sets, convex sets. Suppose you take this, and you can have hyperplane, but that will not be the case always, right? But if it is bounded, if at least one set is bounded, you can always find a hyperplane. But if both the sets are not bounded, unbounded, you may not have a hyperplane which will separate. Yes. In R2 you can. Yes. Cannot be separated. So these are two results of separation, but there are some more results related to separation, like if you have a set which is open, what will be the case if the set is open and then the point is on the closure of that set, right? You try to find out if the set is open and the point is on the closure of that set, then how you can find out this separation of this set with this point? I mean, you can have the variations, different variations, and try to find out that which result where we are using and how it is useful, right? So maybe we stop this time, and then if you have any questions you can ask.
In this case, we get a hyperplane to separate this two
Okay,
sets.
okay.
But in this case, this is
Yes, very good. So you cannot have this, right?
but
But both these sets are
y-axis will be
convex.
separate, but not strictly separate.
No, yes. So this is the point. So both these sets are convex but unbounded.
Yes.
So that is why you are not able to find out hyperplane. In this case you can find out. It's not that it will never find, but if it is bounded, at least one is bounded, you can always have an hyperplane, right? Okay. So then we will meet tomorrow at 10. We will continue this discussion, and if you want to have your assessment of this course, then you please fill the form, and maybe from Saturday we will start the assessment. So it will be like for the first 2 lectures there will be one paper, multiple objective type, right? So for day 1 and day 2 there will be one paper, then day 3, day 4 there will be another paper, like this. Okay, so the first test will be on Saturday, and I will declare the time to you. Okay, thank you.